recommend you all see it so we can have a discussion about it. So I think, is it still playing? I hope it's still playing in California maybe or something. American Nova is still playing locally? Yeah, pretty sure? I recommend you all see it because I think it'd be really great to have a discussion about it at the end. We have a little bit of flexibility with our lecture schedule at the end to have some fun. Like there's one lecture that's basically an open lecture. And I want to basically completely make this course about you and responding to what you care about. So if you say, that last lecture I'd like to hear about opportunities in CS where you can go after this, we'll do that. If you want to have all of us get up here and you ask us any question you want to about how does this work, we'll have a lecture like that. If you want to actually have an in-class discussion about the movie social network, I think that'd be really cool too. Okay? So please all see that by the end of the semester. I think there was even a momentum on our TAs to have a group class visit where we somehow supplement a little bit with going to see it, which might be a nice thing. So we'll talk about that. But if you want to do that, would that be interesting to you to have us organize a big class party to go see the movie? And then, all right, so John, I need to give credit where credit's due. Our TA was leading that discussion, so I want to make sure that, I should turn the lights on so that the screen is poor contrast, but the video shows up well. You have handouts, by the way, so that should be OK. All right, my clock says 11:10. Welcome, everybody, to, what are we on? Lecture 19. We're talking about distributed computing, and I always try to have, as I say, a technology in the news segment. And what's interesting is I was away in DC. How about that for being away in DC I missed, unfortunately, the Jon Stewart Sanity March. But I was there for the elections. It's fascinating to be in DC for the elections and how different countries, different parts of the country focus on different parts of the election. It was all about the GOP is taking over. It was a refutation of all the progressive politics, blah, 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 blah. And then the Giants win. Like all happening with me away. Like what? How many more things? A birth of my 7th child. I mean, all these things are happening with me. No, joking. With me away, allegedly. So here's the thing. We have the news of GOP spamming on Twitter. We had a Twitter lecture. And GOP has now swept many of the country's elections. Turns out that there were some deceitful practices. The GOP, now I wouldn't say the GOP like led from above, but there was movement. Researchers at Indiana University found that there were lots of false Twitter accounts set up, all to give the impression of a broad grassroots movement. And this link could tell you a little bit more about that. But they basically, here's the network graph, and they said, this looks a little fishy. And they looked into it, and it turns out that there was the same message was being sent by many of the same things, like in too fast for someone to read it and copy and paste it into their own Twitter account. So it was all kind of bot done as a program to do that. So it was kind of a not so cool, but and who knows how much that affected the movement. But anyway, the election. But just some updated news. So the overview today, I'm going to kind of have different hats. We're going to do some basics where I teach you a little bit about memory and networking, a little bit about systems. Then we'll talk about distributed computing, and then we'll do this cool demo about MapReduce, which is going to be what you'll do in lab. People in the past, of your feedback, have said we want to have a closer tie-in between lecture and lab, and that typically happens for technical content like this. It happened during your higher order functions and Lambda stuff, and it's going to happen again today. It also happened during your recursion stuff. So, memory hierarchy. So big picture of how you should think of a memory is you've got a processor. We've talked about what a processor is. You might have multiple cores on that processor, but that is the kind of top of that is the brains of the system. And we have what we call a big triangle or a hierarchy of memory levels. This may not make sense until I give some examples. The size grows bigger as you get farther away from the processor. These are called the levels in the memory hierarchy. And that's the lower side. This is the higher side. So the lower, even though the number is bigger, it's a little bit weird. But, and this is increasing distance. This is what we call physical distance from the processor. So for example, on the processor, level 1, actually on the die, there is a little bit of space for storing stuff. That's called a register. It's really fast. Okay? You don't need to know that name. I'm just going to tell you. Okay? Now let's go to the next level. The second level is something called a cache. And that's also often on a die. And that's bigger. Let's look at it. It's bigger and slower. Okay? The next slide says if it's closer to the processor, it's smaller, faster, more expensive, and also a subset of the lower levels. I mean, what's a subset? You may know set theory? You may know in math. What does a subset mean? Any love? I didn't hear. Somebody give it is a set within a set. It is the larger area has, like here, has everything. And then this level n minus 1 has not everything, but some collection of, not everything, but some set of it. Okay, some subset of it. Okay, a smaller, the same stuff, a copy of the same stuff. And then the smaller you get, it's some of the same stuff, but the more important and more recently used same stuff. Until you get to the level 1, which has only a couple of things, but it's the stuff you're using a lot right now. Okay, so smaller, faster, more expensive, and a subset of the lower levels. So the second level is a cache, we call it. Name not important here in this class, but it's a cache. Slower, less expensive than registers, memory, the amount of memory used for registers. And then this might be several levels of cache. Then somewhere in the middle you have actual memory. If you went to Best Buy or to your Apple dealer and said, I want more memory in your computer, that's this middle level. And then below that, we often have a hard drive. A hard drive is much bigger than the memory. And the memory is much bigger than the level 3 cache, which is bigger than level 2 cache, bigger than level 1 cache, which is bigger than the register at the top. The idea is here's the most important part of the whole reason for the whole thing. Here's the thing. There's a wonderful abstraction. This abstraction is so powerful, and the reason we do this. From the point of view of the processor, I'm the king processor, I look down and I see memory. I see, scratch space, place to store my data. Okay? That is as fast as the smallest triangle, okay, as the highest level. Stay with me. Thank you very much. Excellent. But as big as the lowest level. I'll say it again. This abstraction allows you to lie. You are lying to the processor. You're telling the processor, see this top level? It's all the benefits of the top level in terms of speed, in terms of speed. Speed is the real benefit. Look at the things. Speed and small. Small's bad. Okay, more expensive, bad, and subset, bad. So all those things are bad. The best thing is speed. So you're as fast as this guy, but you're as big as the guy as the bottommost guy. So you're as big as disk, but you're as fast as this little register that's really fast. That can be operated that can be read and written to more than 1 billion times a second. Okay? That's not real. That's not true. You cannot read and write to disk 1 billion times a second. But because of having copies of things, because of this idea of the subset, the abstraction from the point of view of the processor says, oh, you mean I really do have memory the size of a disk, but as fast as this top level register. That's really powerful abstraction, and one of the most important things of all of that. Is there anything below that bottom level? Is there anything bigger than disk? When you want to back up your hard drive, what do? Maybe an external larger hard drive. Okay, great. One below that one. Where do you back that up? Maybe a network. Maybe you might go to the network behind that. Maybe a network, a cloud. Maybe you use the cloud. A lot of hard drives, like a Dropboxy kind of thing for a bigger system out of that. It's pretty cool. So all of that tells your processor, tells your computer basically that you have access to all of that data, even on the cloud, as fast as I can get to it, as if it were on my die, which is incredible, which is more than 1 billion times a second. Okay? Really powerful abstraction. That's memory. And that's relevant because we're going to talk about the cloud as maybe part of that memory hierarchy. Okay? So, networking basics. The idea of networking is the following. I have two computers that want to talk to each other. And at the very simplest level, I just want to send from sender, source, to destination. And you're going to go through this internet cloud. And the basics, this is such, I'm taking an entire field and boiling it down to 2 slides. This is how crazy this is in terms of just sweeping all the details under the rug. But here's from 10 miles up, what you need to know about networking. You've got an internet. This internet allows computers plugged into them that didn't know about each other before. Like a second ago, my computer wasn't plugged in. And all of a sudden, I plug it in. And somehow, it's able to send a message to another computer. On each computer, you have what we call a NIC, or a network interface card, or here, a network interface device. It's like a card that basically can talk to the network. And my computer can talk to this network interfacing device, or my NIC card. So I have source, I'm sending a message to destination. I say go. In that message, I have encoded what the address of where my destination is. And here's the best part. That gets sent through the network, that gets sent through the internet dynamically. There are lots of, the word is, switches and routers. Okay? A switch essentially says many things plug into it, and it's almost like the operator in the olden days where you'd say, yeah, I need to make a phone call, okay, and it would take a wire and connect this guy to this guy, right? In the olden days, there was 2 wires. You ever see those movies? No love? Yeah, some love, okay. So it'll take the 2 wires, make the cord, and it would go, okay, you want to talk to Jones? Okay, Farmer Jones talking to Farmer Smith, Farmer Jones, Farmer Smith, okay, you got it? Okay, good. And then Farmer Jones is connected to Farmer Smith, okay? That's, in a very high level, what a switch does. Many different nodes coming in, and it actually makes the electronic connection to go from one to the other. A router has a little bit more intelligence. A router is going to be somebody to decide how to send it. So this might end up, for example, I might want to send a message, let's say, to the back of the room. But I can only send it from person to person. I can't just yell to the back of the room. Well, in the past, if I've ever sent a message to that area before, there might be, at every single router, they know what the best route is. Like if I said, how do you get from here to another distance? You'd say, well, normally the highway is really good. So get on I-101 as fast as you can. So there's some previous history, which is encoded in a routing table. This is a good new thing I just thought of to add to the slides. Routing table. That routing table is what stores what the best route is for each of those routers. Now, every once in a while, that routing table will be updated based on the fact that, hey, I sent some messages and I got no love back. So maybe that route isn't so good anymore. So maybe update the routing table to kind of have a more efficient way of doing things. So that routing table is kind of a memory of what the best way to send it through the network is. And that's dynamic in some sense. If all of a sudden, let's say all of one state went down. This is what's so cool about the internet. If all of, let's say, to go from here to the East Coast, you're geographically going to go through the middle of the country, right? Let's say all of Kansas and the neighboring states went down, middle of the country. And let's say before, all the messages have been routed through servers in Kansas. Well, dynamically, it would try to go through Kansas. No love, no love. All right, let me try some other ways. OK, yep. These are now alive. And dynamically, the internet would route around the problem. It was built into the system to not be bombable. You can't have the bad people throw a big bomb at one of the sites and take down the internet because it'll route around the problem site. It's unbelievable how dynamic it is. You cannot bring down the internet except if you use these worms and viruses. That's kind of get a sickness inside the health of the system. But physically damaging one of the things, it'll route around that. It's really pretty powerful. Okay? So all of that is what the basics of networking are. Here are some big ideas that if you step back and say, that's how networking works in some sense, 10 miles up. What are the important things you walk away from understanding about networking? Well, it's not just connecting computers. Networks also connect other networks. That's what's really cool. You kind of make a hierarchy of the networks themselves. They connect people all over the world, connect computers all over the world. You know that. That's a silly thing to say. You all know that. But they even connect to space. The space station actually was able to send data back and forth. So in theory, space is still part of the network. You can, in theory, get to a machine. It's probably some security stuff. But in theory, that machine in space could lock and see a website from Google down here in Mountain View. That's pretty cool. And even the websites at Mountain View, even though Google's headquarters is in Mountain View, you're not actually visiting their website served from Mountain View. You're visiting served from some data center somewhere. And that might be even in another country. It's amazing how this all works. So it really is the case that you think, oh, every time I go to Google, it's going to Mountain View. It's not. It's going to some data center. Depending on what the load is, dynamically, it's going to some other site, which is really pretty powerful stuff. Here's another big idea here. The networks support communication. You obviously know that you're using social networks and email and file transfer and all that stuff in the web. Asynchronous means it doesn't have to say, well, let's make sure we're both online at 3 o'clock. OK, ready? Send the file. OK, got it. All this is happening asynchronously without any synchronization at all. Synchronization means like the same time, same step. And also, new forms of collaboration are coming up, and you all know that. Amazing new forms of collaboration based on these networks. So it's an amazing thing. This internet thing comes around once in a lifetime. It's one of the most important inventions of our lifetime. It's pretty exciting. So I'm going to now channel back. I'm done with my basics now. Now we're channeling back to what Kathy Yellick was doing. Professor Yellick was talking about using computing to save the world. And this is talking a little bit about that, and kind of this is all review. But let me just show you some of the numbers we have in terms of why can't I do that work on my home computer? Well, let's look at that. she talked about what a floating point operation per second is as a measure of performance for these scientific calculations. Okay? So global climate, she talked about that and the requirements for that. If you want to do weather prediction in terms of this, how much power you need, how many flops you need 56 gigaflops, which will allow you to do 7 days with this global climate simulation in 24 hours. So that basically means you can go a week ahead in a day. Right? So yesterday I ran a simulation which predicted a week ahead, and I'll give you what I believe. And I'll give you a month to come up with that. You know, maybe you come up, here's a new model. Let me see what happens if I try this new way to have heat transfer between the nodes. Okay, go. And so I would wait a month, 30 days, and I want to be able to look ahead 50 years and see what that looks like in terms of prediction. Okay? And then, oh, what happens if we cut emissions by this much? Well, it's OK if I wait a month to get those results, because it's so important. Okay? That requires 4.8 teraflops, an incredible desire for power right there. 4.8 teraflops, that's what you need to get those numbers. 50 years and using that model in 30 days, that's incredible. How about perspective? I updated these numbers based on the fastest machine you could buy right now. If you said money, I remember the Jurassic Park, money is no object. So if you said, we spared no expense to buy the fastest machine I had now, how fast can you get? The fastest machine right now is the Intel Core i7-980XE desktop. So one machine on your desk. How many floating point operations a second can you get? 100 gigaflops, which is incredible. That number is incredible. This is the number that supercomputers were doing maybe 15 years ago. People were paying more than $1 million easily for a computer that was doing this, and now you have it for maybe 10,000 or something, however much a high-end machine what that is. It's incredible. It's incredible what the computer revolution has done for us. But let's look at this. Well, this is like 50 years in a month, and 100, and this is 4.8. So it's kind of like 48 times that, so 48 months. That's about 4 years. So it means, let's see what this new climate update is. What if you cut emissions by that? Well, we're basically waiting 4 years to get that number if you use a desktop. That doesn't help so much to make, decisions. That's enough. Let's wait till the next president is in office before we tell them the results. Right? That's essentially what you're doing. So the need for processing power is certainly evident. So what can we do? A lot of CPUs. And I decided to divide, I think the world has decided to divide systems of many CPUs into kind of two categories, very roughly. One is called the supercomputer category. And it's a little blurring because of what's happening down here, but I'll talk about that in a moment. But in the olden days, a supercomputer was usually a really rare architecture in which you had a lot of high-speed connectivity between where the memory is. It wasn't just, here's a computer, and here's a computer, here's a computer, and I'm going to have them talk over the network. You had to have a more interesting architecture, a more sophisticated architecture to be able to have data go from kind of processor to processor. It wasn't just, here's a box, and here's a box, and here's an Ethernet cable. It was something much more sophisticated than that. I called that the exotic architectures, and that was typically the supercomputer space. Okay? Distributed computing says that's everything else in the terms of multiple CPUs. So that typically is a rack of servers that is either in a category of a grid or a cluster. Okay? A grid says, I have no idea what's out there. Who's ever used SETI at home? SETI at home, who knows about SETI at home? The idea of SETI at home. SETI at home is you can download a screensaver, you download some work, and your screensaver will chunk and try to find signals and maybe listening for extraterrestrial intelligence from some radio data, radio transmission data, radio telescope data. Okay? So that is, the people SETI at home have a screensaver. Do they have any control over what computers that screensaver is being run on? None, right? Whatever you have, however many Macs, PCs, Amigas, crazy systems you have, 286s you want to run in SETI at home, go for it. Have some fun. Okay? So a grid is a heterogeneous world where you have lots of different computers different. A cluster says mostly the same. Basically, you're going to have a data center with all the same kind of computer. It makes life so much easier. Data centers are what Armando Fox is going to talk about on Wednesday. And kind of that's what happens with thinking about data centers, where you have Google and Amazon and other folks just buying huge warehouses and pulling trucks up and having all the same. This truck has maybe 100, maybe 1,000 machines all in one truck. And you pull out all these little, it's like the freight cars, what are those called? The freight freight thingies, the things that are on the Oakland docks, the freight. Containers, they call them containers. The freight containers, full of 1,000 machines each, and you put a lot of these into a big warehouse, you cool it, you get power to it, and there, my friend, is a data center. It's pretty powerful stuff. That is kind of a cluster. Now, why it's weird is that the supercomputer world, Kathy Yellick's stuff, people doing it on the top of the lab, they are moving toward a cluster-based approach because it's cheaper. All their machines are just clusters. They may have special ways to connect memory to each other, but for the most part, they're just doing a cluster. And here's the bottom line here. It's not about solving small problems faster. It's about solving really big problems where you need a massive amount of compute horsepower or a massive amount of data that you're working with. Okay? So here's some themes. Okay? So let's put all these things into one cluster. Let's network all these things together into one compute cluster. Put a virtual bubble around it called that's one big compute cluster. And we can do that now. And if they're the same machine, it's really easy. If they're different machines, it's a lot harder to deal with all the kind of differences in the machine architecture. A common theme is you have a dispatcher and you have a worker. The dispatcher is somebody who, like a taxi dispatcher, somebody who starts the process. Ready? Go. And all the workers are all worker bees. And the easiest model is all the workers are the same. You just send it out to all your workers. They're all the same. They get some work and they come back to you. Okay? There are a lot of other themes. There are a lot of other parallel programming paradigms, nice alliteration there, in which you have different models of getting data to flow to each other. That's kind of cool. But the simplest one is the dispatcher and worker model. Okay? So here's some examples. SETI at home. BOINC is Berkeley, I don't know what the OI stands for. Infrastructure for Network Computing. I don't know what the O stands for. Render farms are what people do at any of the high-end companies like Lucasfilm, also in the Bay Area, or Pixar, or DreamWorks, also in the Bay Area. They have big render farms to render their movies, and Google Cluster is running MapReduce. So we'll talk about that more today. So now I'm going to plug this in. Take a second to get your clickers out while I plug this in and get my clicker hardware ready. And the questions are, and think about it while I'm plugging in. Question number one, you're actually going to answer 2 questions at once. Okay? Shh. Okay, 2 questions at once, folks. Here we go. Question number 1. That's the answer. Good. That's the answer. All right, good. That was not so good. Dan, hope you weren't looking and getting your clicker at the same time. That happens every once in a while when I don't hide a slide. Okay. Writing and managing SETI at home is relatively straightforward. Just hand out and gather data. That's SETI at home. And 2, the majority of the world's computing power lives in supercomputing centers. And let's see how much I affected the vote by showing you the answers.
You said relatively straightforward for number 1. Is that relative to BYOB?
Yeah, relative to BYOB, a little bit harder, with a little bit more. BYOB plus a little bit more, just kind of dividing up a problem and sending it out and coming back. A little bit more than that. Okay? 43, is that my number? 44? And I'll stop at 45, okay. Still coming in? Okay, talk to your neighbors. This is one of those fun talk to your neighbors ones. So what do you think? Straightforward, majority lives in supercompute centers. Sorry? Oh, yeah. So you need to see the question. Sorry. All right. Come on back. Let's vote again. And go. I probably should move this so you can see. So you're actually responding to 2 questions at once. It's kind of cool. In the olden days, clickers had 10 different options, so I could get 3 questions at once, but the newer clickers have only 5, so I actually lose a little bit here. Option E should be, I saw the answer, so that, why are you asking me again? Okay. So let's see how you did there. and AA, and question 2, and question 1 is AA. So the answer is A. Well done, folks. And here is the answer. Whoops. Here is the answer there. You notice I wasn't on this slide when I went to get out of slide mode. So there was an interview with David Anderson, who was one of the key players, if not the founder of SETI at Home. And he talked about how hard it was to deal with the different architectures out there. You have to write a SETI at Home system for every single machine out there. How hard it was to verify, just the additional challenges of verifying that somebody doesn't game the system. You wouldn't think about this, but there are actually people out there who are hacking their SETI at Home program to download data and then compute, and say, oh, look, I found an ET, and then they return an answer that says, oh, by the way, yes, there was ET. I listened, and the ET was saying phone home, right? And then they go, oh my gosh, ET phone home, and all of a sudden, they would call a national emergency, blah, blah, blah. People are actually doing that. So they have to send the same work unit out to several different people so that, in theory, that person doesn't know who the other people are, so they at least should take a majority vote or something like that. So they might say, well, it's wrong because of their system or because of Big Indian or some weird things about their system. And maybe because they're also gaming it. And the chance that we're all gaming it in exactly the same way is low, so therefore, that would be hard. That's how you kind of take that noise away from the system. So I talked about how hard that was to do that. It's false data stuff. And the second one, the amount of processing power in all the world's PCs, not in a data center, and all of the GPU, the graphics card, has so much processing power compared to the CPU, even for certain kinds of problems, that completely dwarfs all the computers in data centers, which is kind of interesting. Now, the reality is, if you're doing a SETI at Home kind of a thing, you know who's paying for that power? You are. So there's a little bit of a question of, is it more efficient to have a really high efficiency data center with good cooling and all that, and compare what you can get from, say, 1,000 different processors, all in data center, all optimized for cooling it well and for handling it well, than having 1,000 different people do all the work to get that program solved, but then each one of them has a really inefficient system, not built for efficiency, to do a general purpose compute versus something built for specifically trying to get fast horsepower out of the system. So people have said, data centers are really much more efficient than letting this kind of, it's called volunteer computing, take over. All right, so it's false on that one. All right, well done. So let's now talk about challenges. Okay, so that was a little bit of challenges. What are some challenges here? The hard part, it's really hard to take a big problem. I've got a massive data set, and what do? A, I have to think about how to break that problem up. B, I have to break the problem up into small pieces, hand those pieces out to people, to my workers, right? We're not sharing memory. In some sense, you may be sharing the lowest level, which is the network, but you're not really sharing kind of a hardware memory. You're sharing the network. So I have to send that stuff out. I have to wait for the compute. The compute will take different amounts of time. Some people have faster computers, some people not. Even with the same cluster of all the same, it might be that something is weird about one machine, and that machine takes longer than the others for about the equal amount of task. So then I have to maybe wait for the slowest one, wait for that to come back, take all those answers and merge them together. Hard, not easy, a complicated process. And there's all these inefficiencies of waiting for stuff. It's just waiting for the transmission, waiting for the compute, waiting for the slowest machine to come back, waiting for a machine that died. All that stuff makes it really complicated. If a machine dies, I need to either send it redundantly, in which case I'm lowering all the machine. Like efficiently, if no one was going to die in terms of no machine was going to crash in terms of all of the machines working, I could send it all to all of you and then wait, and they'd all come back at the exact same time. That would be fine. That would be maybe the most efficient way of doing it. But that's not the reality. Some of the machines are going to crash. Some hard drives may fail. Some memory may fail. So I have to either send the same thing to the left as the right, and then maybe one of the two of you will do it. But then all of a sudden now I've reduced my kind of potential CPU utilization by half by using half of you to do the same computation that the person on the left side of the aisle did. That doesn't make sense. But maybe you have to use some of that to be able to handle this dropped machine. Or maybe you wait a certain time until it comes back. But then waiting is another open problem in terms of the waiting, in terms of what's called the halting problem. So how long do you wait? Maybe it's going to answer any time now. All those things are hard. So you want to look at problems that are massively parallel, like rendering this. This is a really massively parallel problem. The geometry is really small. here's some balloons and maybe some really geometric way of saying where the balloons are. Here's some geometry. This house might be a little bit more detailed. Maybe his face is detailed. But if I say render this at a really high resolution, that's a lot of time that can be spent doing the rendering and not necessarily looking at the data. So you want the compute times to really be much larger than the overhead for doing that, the overhead for shipping the data out and coming it back. Otherwise, it's not as useful. So welcome to MapReduce. Welcome to a hopefully great way, a new paradigm for programming things in parallel that's going to try to address all the problems I just said. I just said it's really hard to write in parallel, right? Not if you use the right abstraction. MapReduce is a parallel processing abstraction, otherwise known as a distributed computing abstraction, that is really awesome and really wonderful. We've simplified it even further. So MapReduce is already pretty simple, but already past that, we have taken it and simplified it enough to put it into BYOB, which is pretty cool. So the same idea that you could use to program 10,000 machines, this interface is all you need. And that's really, really cool. So we already talked about, Brian talked about functional programming, and the beauty of that is that each function, each block, each reporter, if it's a pure function, doesn't have any side effects. Its input is only a function of its input and not of any previous state. If that's the case, you can parallelize that. And that's part of the beauty of higher order functions. It's part of the idea of BYOB, is sharing that idea with you. Okay? So you've got a mapper and a reducer. Hopefully, thanks to last week, you know what a mapper is. Remember what a mapper is? You do something to everything, right? Everybody say your name out loud. Ready? 1, 2, 3. Say your name. Okay, don't do it. But that's what a map would be, right? I call the say your name procedure on, I map say your name to whole class, okay? A reducer somehow maps all of that together. So if I said, I want to figure out what the average age of everybody is, you might say, well, what's the mapper for that? If I take that problem of finding average age into a MapReduce paradigm, what is that? Well, map might be, all right, for each person, look up your age and return that. That's what the mapper does. Reducer might say, take all those things and reduce them down so that you have one number. And that's the average age of everybody. It's a reduction of a lot of stuff to one. Okay, that's what a reducer does. Okay? So here is the, I'm going to turn a lot just for this one because I think it's important that you see the screen a little bit better for this one because I want to make sure you see this. All right? So how about this? Let's now zoom in. Oh, here's a summary here. 10,000 machines are going to help you with this. When you fire up MapReduce, in theory, behind the scenes, 10,000 machines wake up and help you with that problem. Okay? How is that possible? What if I had, let me just show you, let's go to an example and see why it's easy to kind of do that. So here is the interface. Map block, map a reporter block, reduce reporter block over a list. That's it. That's as hard as it is. From now to the end of the lecture and in 2 hours of lab, you'll just do nothing but this. That's all you're going to do. That's how simple and beautiful this is. So let's look at this. Here's how I wrote it. I wrote it with built-in functions, built-in blocks. Map, mapper, reduce, reducer, over list. Those are the arguments, okay? What does it do? Reports. First, it says map the mapper over the list. That is now itself a list. That's the list of the result of all those things, okay? The list of the result of all those things, all the mapper on each of the elements of the list. I get now the list of results. And then I combine with reducer. That's it. That's the whole thing. Now you're going to say, where's the parallelism, Dan? Well, let's look at an example. Map, here's how I call it. Map of multiply, reduce of add over this list, 1, 20, 3, and 10. Mapper takes a one-argument function. Reducer takes is a one-argument reporter. Reducer is a two-argument, because it's going to combine 2 to 1. It's going to do that multiple times. There's a cool BYOB feature, which is if I pass in one argument to something that takes 2, it'll copy the argument to both holes, both of those input holes. So this becomes a square block. Does that make sense? Because I'll take my number and copy it both times, it'll be squaring it. Okay, that's just a side effect. So here's actually what happens. So here is my input. 1, 20, 3, and 10. Each one of those is affected by a mapper. My mapper is multiply. Multiply by itself, really, what it is, okay? So it squares it. And now I have the 4 squares. Can you see how that can be done in parallel? Everyone should say, Yes, Dan. Each one of these things could be a different machine doing all of that. So mapper, the parallelization of mapper is really easy, right? You just divide up to all the machines you have and just go. You say, well, Dan, what if I have fewer things than machines? That's fine. You'll just, if I have 10,000 machines, but I only need 4 different machines, I only use 4 of them. But Dan, what if my list is 1,000,000, but I only have 10,000 machines? What do you think happens then? A list of 1,000,000 things, but only 10,000 helpers. Yeah, I split 1,000,000 by 10,000, but essentially I have a lot of map tasks. I actually still have 1,000,000 tasks. And the 10,000 machines will just take them one by one and grab a task, finish it, and grab another one, and then grab another one. Does that make sense? It's like a taxi going off and doing some work, and then doing some work. Dispatcher telling a taxi, go pick that person up. You done? All right, pick another person up. You done? Pick another person up. Keep doing that, okay? So if I have 10,000 machines, each machine will just keep chugging as many of these work units as they can until you're all done with all of them. That make sense? Okay. How about the reducer? Well, here's my reducer. I am somehow making a tree by taking 2 to 1, and 2 to 1, and 2 to 1. And you don't in advance know how that tree is set up. I drew this in a perfect, nice, NCAA binary tournament, right? Like a nice, pretty binary tree. The world isn't like that. These 2 might return. Let's say I had 10 different things. These 2 might return. Then 2 over there might return. And then I combine those 2 over there. But Dan, they're not together. They're supposed to be together, right? No. The most important piece here is that your reducer, I wrote it here, should be associative and commutative. Associative means you can cluster them in any pairs you want, as long as they're in the right order. Commutative says flip them out of order. And if that's true, it doesn't matter what order the 2 things come out of. As reducers get done and say, hey, anybody need a reduction? Oh, this too? Okay, I'm a free machine. I'll grab it, reduce it, and give it back to you. And that may now feed a reduction of somebody else. So the tree isn't necessarily as pretty as I've drawn it here, but as long as your reducer is associative and commutative, it'll be fine. Okay, so far? Also, when I describe this process, there's only 2 different data types I need, and I colored them here. You say, Dan, I want to do a MapReduce job. I say, great, what do you want to do? Oh, I want to do some kind of, and it's garbled over the phone. I can't hear what you say. All right, I don't know what you're saying, but sounds good. Sounds good. I bless it. That's fine. My next question might be, what's your input and what's your output? The input is a list of something. Input has to start with a list, right? Because mapper attacks a list. It can be a list of something. Here's a list of numbers. It can be a list of anything. It can be a list of lists. It can be a list of procedures, list of blocks. It could be a list of words. It could be a list of sentences. That's the first input. That's the first data type you have. What's the input? And the last part is, what's your output? But notice, there's some missing variables in here. But Dan, that mapper, each mapper has its data type that it returns. Let me show you here, take with my cursor. Each mapper has its data type. Each reducer takes 2 types and returns another data type. And then the last reducer returns something. And I say they have to all be the same. All those things in yellow have to be the same. The output of the reducer has to be the same output of the reducer, the bottom guy. The last reducer has to be the same as the output of any other reducer. Has to be the same as the input to the reducers. Has to be the same as the output of the mappers. Why? Why is there a constraint on all those things being equal, being the same exact type? Because it's in the picture, so it can be parallelized. But even without being parallelized, the way I tie them together is like this. If you have only a single list of one thing, do you need a reducer? No. Why, Anna? To one thing. So no reducer needed if I only have one thing. So therefore, you know, because of that fact, that the output of the mapper better be the same as the output of the whole thing. So you know this matches this because of that, right? You know that the output of one mapper better be the same as the output of your final program, which is the output of reducer. So those 3 are the same. How about the input of reducers? The input of reducers is the output of the mapper, so that has to match for that reason. So for a couple of equation reasons, you have all those types in yellow have to be identical. So there are really only 2 types you care about. Normally, by the way, if I have 2 functions, a mapper and a reducer, there are 4 different variables. What kind does the mapper take as input, or the domain? What does the mapper put output, or its range? What's the reducer's domain, or input. What's the reducer's range or output? 4 different types. I'm saying when you plug them together like this, 2 of those have to be the same. So you only have flexibility on output of the reducer and input to the mapper. That's all you have. So if I say, let's make a problem, let's do something. You know, oh, okay, well, what's the input? It'd be a list of something. That's the input of the mapper. That fixes one of those constraints. And what's the output of the whole thing? What do you want it to do at the end of the day? That's the result. And that's it. Everything else is constrained for you. You say, but Dan, you didn't tell me what the output of the mapper is. You know what the output of the mapper is. It has to be the same as the output of the reducer. You didn't tell me what the input of the reducer is. You know what that is. It better be the same as the output of the reducer. Does that make sense? OK. So let's now look at an example. Here is your project you're going to work on in the lab. And here's a picture of Cal. And this is actually a scratch we inherited from BYOB costume. Here's a person with a Cal Berkeley shirt on. Go Scratch. Love it. Like a little hidden Easter egg with a Cal Berkeley sweatshirt on. Love it. Marissa, is that right? Melissa? Marissa?
Yes.
Some Issa at the end. OK, so here's how this works. You boot this up. This is all you have to do in your lab. You have to say start to initialize everything. And she says, type any number 1 through 5 to run a MapReduce example. The output will show up on the list on your right. So I'm going to zoom in a little bit over here. Rather than show, it's kind of funny, actually. If you run this in presentation mode, it runs everything as atomic. But so there's a little wait I have in here, which it says going, processing, and then says answer. It'll say like processing, done. If I run in presentation mode, she waits for the whole thing until anything changes. So it's a little different than running it here. So let me run this now. So let's type 1. What does 1 do? 1, I just tell you, is the standard. It's the one we just did. It's the sum of squares. OK? Let's see it, actually. Oh, I don't know. 1. OK? Let me see if I can make this smaller so you can see more. Yink. Look. When 1 is pressed, think running the simple sum of squares MapReduce. Delete all the output as a list of output. Add map of the square guy, reduce of the sum guy over 120, 310. So let's try. Let's see it. Let's zoom back. Let's go over here. Let's zoom in. And type 1. And running, done. 510. Yay, 510. It works. MapReduce. OK, so far so good. The next problem. The next one is alpha. So alpha. So the alpha problem is kind of cool. It is given a list of words. Remember, say, Dan, tell me what the MapReduce problem is. All I'm going to say is a list of blank. That's the input. And the output is blank. OK. It's a list of words. And the output is the word that's closest to the front in the dictionary. OK? Let's work together. What would the mapper be for that? And then what would the reducer be? So remember, list of words, and then the output is a single word. Just one word. That's the one that's closest to the front of the dictionary. How will we write this together? Let's brainstorm. Give me somebody brainstorm how you would write this into a MapReduce framework. Part of what I want you to do is be able to say, I give you a problem, and you figure out how to break it down to a mapper and a reducer, or say it's impossible. OK? So how do we use MapReduce to help us with this? What would the mapper be? What would the reducer be? Trying to find the word that's the first in a list of words. What's cool about this, by the way, is if you can think this way, you don't have to write any. We talked a little bit about declarative programming being so cool and so powerful because you don't tell it how to do it, you tell it what you want. In some sense, MapReduce is like that. If you can think of this in a MapReduce program, you just say what a mapper should be and kind of how to take 2 to 1, and the whole thing just works. You don't have to tell it explicitly for I equals the first word to the last. All that stuff is done. That's all old school. Once you start thinking in this higher order function way, it's so much more powerful. People just say what it is, it just happens. It's very much a declarative way of thinking. All right, work with me. Volunteers, I'm trying to find the alphabetical closest word to the front of the dictionary, given a list of words. How do I map it, and how do I reduce that? Give you a hint. Do you have to do anything to the word? So for each word comes through, do you have to do anything to it at all? Okay.
Put each word into a list, so you can manipulate each word.
Okay, each word, right? Each word is in a list. It starts all the words are starting a big list. They're all together.
We have to manipulate the string so that one word is in each element. So.
Here, let me give you a hint. Look at this picture and see if on the bottom right of this picture you can think about how to make that picture come up with, like, imagine, like, I have, I love CS10. 10 is not a number, but it's weird. But anyway, I love CS10, okay?
You had a list of 4 elements, so one word per thing, and then you can use heat seconds.
But it has to be in the MapReduce framework. Whatever you're doing, it has to be in the map. It's all MapReduce. We're talking about how to make that problem into MapReduce. Well, you always got to map first and then reduce. But your mapper can just do nothing. Your mapper can just be the identity, which returns the same word unchanged, if you want.
I'm just thinking that you would compare the first one to see which one has
Oh, I like it. Compare some things.
and then just delete the one that's not going to.
Just keep the one you. Oh, exactly. It's like compare two guys and return the one that's closer to A, maybe.
Yeah.
Right? Is that what you're going to say? That sounds great so far.
You could assign like a numerical value to each word depending on
Where it is, maybe in the thing. Yeah.
and then compare those.
That's true. That's true. That might be. That's actually harder because you're adding another level of the number and then going back to the thing. If you could just, if there's something that'll let you compare two numbers, the less than symbol actually works for words. It already works for words. You can say alpha as less than beta, which is kind of cool. Do you have an idea? Yeah.
I didn't know what the ASCII or
ASCII. Yeah.
ASCII, could you use that to assign to the
You could use ASCII. You could. That's part of the same comment of kind of making a numerical connection with that. But because the less than symbol actually works for words, you don't actually have to go in the complicated ASCII way. I'll give you a hint. Mapper does nothing. Mapper returns all the words together. So that this top level of yellow is I love CS10. And you're saying, I want a reducer. Say reducer out loud again. It takes two words and reports the word that's smaller, right? The word that's closer to A. That's it. That's it. So let's compare. Mapper does nothing. Mapper takes an argument and passes it right through. It's the identity. The reducer takes two words, looks at the two of them, and returns the ones closer to A. That's all. Guess what? If you had passed in, now think for a while, you're using a Google data center, and I ask you to compare all the words ever written by mankind and find the word that's closest to A, like the one that's like aardvark, or whatever that is, okay? The one's all in the front. Quadruple A towing or something, they always do that, right? That would work. All you did was identity, which is no work at all, and this reducer, which is compare two guys and return the closer one to A, that solves it. Let's do it. Here we go. Here's alpha. Here's alpha. Set input to be or not to be, that is the ahem question. Okay? See what it says? And I call sentence to list, so I make a list of all those words, okay? Let's try it. Here we go. I hit 2, running alpha MapReduce. Ahem. What was now each of these, by the way, each of these sprites down here has its own internal reporter block. When you make a new block, there's an option you might have seen before, which is make this block global for all sprites or only local for this sprite. Ever see that button? For each of these, I've said local to this sprite only. So now I go into the mapper. What's the mapper do? Let's see how complicated that guy is. Oh, that's hard. Mapper word, return word. Does nothing, right? How about the reducer? So go over here to the reducer. Look at this. Is this hard, folks? Tell me that's hard. Come on. If word 1 is less than word 2, return word 1, report word 1. Otherwise, report word 2. That, on 10,000 machines, on the corpus of all of human written language, would have given you the letter closest to A. Isn't that crazy? That's the beauty of thinking in a MapReduce way. You're going to spend time doing that. You'll play with love. I kind of gave you the answer to the first one. So that was a little bit helping you with your lab. There's alpha. I want you to write love, and I want you to spend time working word count. Word count is really hard, so get started early, okay? Last slide. Advantages, disadvantages, I talked about before. MapReduce, you don't need to worry about failed machines, just handles it for you. It handles all the distribution, all the load balancing for you. It's awesome. Hadoop is an open source version of that. There's a clicker question that we don't have time for. In summary, MapReduce is awesome. It's an amazing distributed computing abstraction. And systems and networks are really, really important towards moving forward in an information technology world to allow for collaborations, inventions. It's the fundamental building block of our society. It really is going to be. Social networks, all that stuff. See the movie Social Networks. We'll talk about that near the end of the semester. Enjoy lab today, guys.